So you've done the ramp lab today, and our goal is to sort of understand what the heck is this acceleration unit about. So you saw something moving and it was gaining speed, and you did a lot of work in class with the tick marks and trying to understand where it was going. And so what this video does is it kind of ties the ramp lab into what our overall topics are for this unit. So if I had to summarize, we've got two main things we want to do. We want to learn how to deal with graphs where there's acceleration, where you can predict motion, tell me what motion is going to look like from graphs, just like we did with the constant velocity unit. And then we're going to actually be working with a lot of equations. So again, just like the last unit, this unit has graphs and it has equations. And the way we're going to get to these ideas is with a concept called average velocity versus instantaneous velocity. And we've already studied average velocity from the previous unit, so that definition is going to stay the same, but we're going to apply it to the ramp lab. And then what we're going to do is we're going to come up with this idea of this thing called instantaneous velocity. And we're going to be using that idea when we look at the graph of velocity versus time in the ramp lab. And then we're going to wrap up with a quick overview of the formulas that we'll be doing, not this week, but next week when we start solving problems with numbers and with algebra. You all did the ramp lab in class today. And so what I want to do is talk about where we're going with the ramp lab and how it ties into this new unit that we're doing. And this week, with walkathon and everything, we're really going to have time to cover some of the qualitative ideas that are related to graphing and predicting motion when there is constant acceleration. So this week is going to be mostly without numbers. And next week we're really going to deal more with the quantitative side of things, which is going to be solving problems using formulas for constant acceleration. And with the ramp lab today, this kind of post-analysis, it's the one video this week where we're really going to deal with both ideas at the same time. For the rest of the week, we're really going to spend our time dealing with the graphs and the graphing stuff. We're going to spend a little bit of this video talking about quantitative ideas, but mostly we'll spend it on qualitative. We're going to do some of the quantitative today, and we're going to really follow up on those ideas next week. So we did the ramp lab, and of course we had the situation of we had this ticker tape, and if you remember, we had these little tick marks, and they would start off really close together, and then as time went on, they'd get more and more separated. And of course, each of these represent the position of the object. So we could call this the initial position right here, and then we have a position x1 and x2 and x3. So even though this is accelerated motion, meaning that we're gaining speed here, what we notice is that this really does tie into that very first video we saw where we're still defining position with respect to a reference point. And in this case, our reference point and our initial position are the same, so we're going to call this the reference point. And we're still marking off positions. What we noticed, though, is unlike the buggy lab, the position seemed to increase with time. We did a little activity with the post-buggy lab where we analyzed data like this. And what we're going to really do today is define a couple of ideas based on what we saw with the buggy lab and tie it to this ramp lab that we did today. So first of all, when we plotted the position versus time, and let me actually just make a little room here and get rid of some of this stuff. When we actually plotted position versus time for this ramp lab, we had a couple of plots that we saw. So we plotted position versus time, And what we saw is that, again, if we plot it with this graph, we saw the dots started off close together, and then they get further and further apart, faster and faster. So we noticed that we started off with this very small slope here, and if you remember, the slope of the position graph gives you the velocity from our last unit. So we have a small slope here, and then here we have a very steep slope. We actually even did an exercise like this in the week 2 learning packet when we looked at the buggy lab part 2. In the lab section of learning packet 2, we talked about a steep slope versus a small slope, and of course this means faster and this means slower. Kind of the new thing we did today was that we actually did a different plot. We did a plot of velocity versus time, and we noticed that we got this situation like this. And what we kind of concluded today was the slope of this graph is the acceleration. And if you remember for the buggy lab graph, we had x2 minus x1. What we have here is we notice that the acceleration, again, it's the rise over the run, as it was for velocity in the buggy lab. But now what we realize is that we have this formula for acceleration that basically says we take v final minus v initial divided by the time that passes. And that's sort of what we're getting for the acceleration. So we get this formula for acceleration that's just a little bit different. And it looks a little bit like the buggy lab formula, but now we're talking about it being for velocity. And we got this formula that was basically v equals acceleration times time plus v naught. We're now on a velocity versus time graph. The initial velocity, this is the y-intercept, and this is the slope. So again, we're talking about a velocity versus time graph. And what we notice is that the velocity is changing. Okay. Now, a really interesting exercise I could ask you is, what does the velocity versus time graph look like for the buggy lab? And in fact, it's actually something I'll have you do either on a quiz or in a Google Doc. But this is for the ramp lab. I want to know, kind of, I'll just write this off to the side, what's v versus t for the buggy lab? What's it look like for the buggy lab? Now, if this is the motion, we actually already learned the definition of average velocity in the last unit. So if I call this point here x final and this point here x initial, I know that average velocity is going to be x final minus x initial over all this time that passes, so from here to here. Okay. Now the question I want to ask, so for example, that would be like, we'll call this x final right here. So that would be, I'd take this position and this reference point, and I'd actually get out a ruler and I'd measure this distance, okay? And I said, okay, I'm going to take this minus that and divide it by the total time that passes. And if you remember, we have like a tenth of a second, so we'd add all these tenths of a seconds up to get the time. And we get the velocity, the average velocity that way, okay? And I'm going to call this average velocity. And I'm going to put a little bar over it. Okay. That's average velocity. Again, just like we did in the last unit. You take your final position, you don't care how you got there. You take your initial position, you don't care, like that's where you start. You subtract the two, so this minus that, and you divide by all this time that passes. Okay, that you're good with. So all this time that passes right here, so you add up all those tenths of a second. Okay. Now what I'm interested in is, suppose I have this point here and this point here, and the question I ask myself is, how fast was the car here? Okay, like in between those 2 points. That's like a tenth of a second. So that's just during that little snippet of time. How fast was the car going? Well, first of all, the word for that is called instantaneous velocity. That's how fast we go at a point in time. And so when I say, and so I want to be kind of clear here, the average velocity is you take your final position and your initial, and you don't worry about the shape of this curve. You just say, you don't worry about the shape of the curve. You just say, I'm going to look here and here. I don't care that this is some weird parabola. I'm just going to take the final initial, subtract it, divide it by time. So that is average velocity right here. For instantaneous, what I'm really saying is, like, if this were 4 and 3, I'd be looking at like here and kind of saying, okay, if this is x4 and this is x3, I'd actually take those positions, subtract them, divide them by that little tiny interval of time there. That's the instantaneous. Okay? We can get deeper for those of you in calculus. We're not going to. We're just going to say that this is the instantaneous velocity. So technically, what this plot is here that you did for the ramp lab, this is the instantaneous velocity versus time. And this equation is the equation for the instantaneous velocity right here. Okay? So that's really what we did. So the purpose of this video is really to help us distinguish between instantaneous velocity and average velocity. And what we're going to really do is we're going to take this idea and we're going to come up with 3 formulas that we're going to be using next week. And I'm actually going to give you a little preview right now. So the 3 formulas that we'll use next week, and we'll actually get into that in a second. The 3 formulas that we'll actually be using next week, they're all for instantaneous stuff, is we'll find that the instantaneous velocity of an object is given by AT plus V naught. That's the ramp lab formula that we came up with today. We're going to have another formula that basically says the position of an object depends on how much it's speeding up by, the speed that it started at, and where it started from. And then we're going to tie these formulas together to come up with the third formula that basically says the instantaneous velocity of an object depends on the velocity it started at, plus the acceleration and its displacement. So we're going to do this stuff really into next week, and we're going to come up with these really from the ramp lab. Okay? This week, what we want to kind of reflect on is we have these graphs here, and what we want to kind of reflect on is that rather than dealing with numbers this week, I want to remind you that position versus time for an object that speeds up looks like this. And when you look at the velocity versus time, it looks like this. And since we said the slope of the velocity graph is the acceleration, and that slope doesn't change for line, the acceleration is, this value is going to be the slope of the V versus T plot. So we've got some vague ideas here. And that what you're going to do is you're going to watch the second video now, and you're going to get an idea of how graphs tell you whether objects are moving forward, moving backwards, speeding up, and slowing down.